Should we wait a bit more? Maybe we wait a few more minutes. I mean, I'm not. It's yeah. Why not? I mean, it doesn't matter. Anyway, I will spend a lot of the first lecture covering some basics, which probably we have had during this week already. But I guess it's always good to start a bit slowly. So I will talk about something which I guess I always like to talk about, which is communication via channels. So we heard already a lot about the different things you can use to communicate via channels. So the main capacities I want to talk about are the classical capacities. So that means you want to send a classical message, the quantum capacity when you want to send quantum states, and the private classical capacity, which is in between. So I will go through some of these notions again, but I hope not to bore you too much. So during this lecture today, I just want to do some very simple and basic calculations. So I think basically all we need is a little bit of some rules how to deal with entropies, phenomenon entropies. And I believe Fernando already introduced a few of these basic inequalities. Oh yeah, so this is supposed to be kind of the overarching theme of all the lectures. Maybe, I don't know if it's enough to stretch it over 4 lectures, but at least for 3 it will suffice. So what it is about is actually in a sense, it's the boring part of the capacity theory. It's this part that tells you that you cannot do better than a certain limit. So the most famous of these limits, I guess, is the Holevo bound, which is one of the earliest results in quantum information. So that is about, it just puts an upper bound, originally just put an upper bound on how much information you can send over a quantum channel. And it puts an upper bound on this capacity, in that sense. So it turns out later on that these bounds that I will show you how to derive, you can also attain them. So they actually, in a certain sense, describe the capacity, but I just want to say the disclaimer straight away that I'm not so much concerned with this part. So the more, I mean, in a certain sense, the more interesting part of capacity theory is how do you actually communicate? How do you show that how do you exhibit codes, for example, communications protocols that achieve a certain rate of communication or a certain amount of bits over the channel. So this I will touch only tangentially, let's say. So the part 1 is just basic. It's just basics. So the fundamental setup, of course, is this one. I treat channels that map states from some finite Hilbert space to another finite Hilbert space. It's not going to be so relevant for most of the discussion that these dimensions are finite and which this dimension is. But I like to stick with the discrete case for most of the parts. So, I mean, it's well known, of course, that there are some things where you have to be careful when you have infinite dimensional Hilbert space. So these are completely positive and trace preserving map, and also in Graham's lecture we saw already that this kind of thing you can so we know that this can be obtained by letting the system interact with an environment, and so kind of stripping away all the unnecessary bits. You can think of, I mean, the only relevant data is an isometry that maps the input Hilbert space to a B tensor some environment or eavesdropper, depending on which scenario we're in. And so then we have also this complementary channel. So this complementary channel is very important in all the discussion of quantum capacity or quantum communication, and more generally private communication, because the definition of the enemy is basically it's E. We want to prevent information from going to E. So the basics are you're somehow given such a box, or rather you have some way of using it many times, right? And many times means, for example, maybe you have many fibers, or you have many successive uses of the fibers that are essentially described by tensor products here. And so to use this for communication, the basic communication diagram is always this one. You have some kind of CP map that is called the encoder, and another CP map that is the decoder. And because it's a CP map, you can stick in any state. So this comes from a space S. So this is somehow the system that we would like to communicate. So the encoder has actually has a number of different functions. One of them is to prepare whatever message you have for these n quantum systems, because they may be whatever, right? Another one is to prepare it for the noise that's going to happen. So because this could be depolarizing noise or whatever. Actually, I guess that's another good thing of having had a number of lectures already. So we did talk about numbers of channels, at least depolarizing channel or phase damping channel. So I guess I will use these words. So you have some state that can come in here, and the state rho hat. And so I don't have colors, but anyway, so this n is given to us. So if you want, we want to find out something about n, about this channel. E and D, these are things that are, let's say, under the control of the sender and the receiver. So the sender is on this side. That's Alice. She should choose this E in an appropriate way, and the decoder should choose D in an appropriate. The receiver should choose the decoder in an appropriate way. The goal, of course, is that this is close to rho. And and so this kind of, I just want to use this to maybe rho hat is not very okay. Actually, to be honest, I tend to use a different. I don't like to use the hats very much for this complementary channel, but I just copied it from Graham because he started doing it. Maybe I do this. So I use the rho hat here not because I want to emphasize it's a density matrix or a matrix, because all of these are matrices, right? No, but I'm using it in the sense of a statistician. The hat is somehow the estimate. If you give noisy observation data, and if you want, the Bob here wants to learn about rho. And so the way we formalize this, he wants to reproduce the density matrix. So, sorry, classical. So why I'm drawing this is only to emphasize that at least the basic capacities of channels, or the basic tasks, we can understand all in the same communication diagram. And for example, for classical communication, we will simply demand this only for specific states, namely a computational basis. And M goes from 1 to, let's say, well, the dimension of S. So this is the dimension. And of course, we have to specify this approximation, which I will also do. Unfortunately, we have to be a bit more concrete about which metric we use here, but I mean, it's going to be later. So private, it's the same, but also you want that what did I say? The complementary channel output of rho. So this is a state that is in e to the n, right? So we have here, we also have some kind of E1 to En. comes from this here, the environments, this should be close to some constant state, omega 0 on e to the n. Yeah, so it's the same thing but with an extra constraint. Bigger, okay. Of course. And quantum, we would like to have this basically for all state, for all rho on S. And just want to introduce some notation here, or some jargon. So the things that we use from Shannon theory, this n, we call it the block length. And so the regime in which we are usually discussing this kind of theory is when n goes to infinity. and here, and here, this requires a metric, as I said. And there is some kind of epsilon that we call the error. Yeah, so the metric, the epsilon metric distance, this somehow quantifies how different these kind of things are. And so the objective of what we are trying to do, or at least one way of looking at it, is for given n and for given block length and error, what can we say about the size of this system here? So this S here, this is, or rather the dimension of S, this quantifies in some sense the number of messages, even in the quantum case, because it's the dimensionality of the quantum system. So the log of this is number of qubits, as a function of n and epsilon. So you If I'm going too slow, please tell me. So let's look at, for example, what I'm really saying here for example, for the classical capacities, for the case that all I want to send are basis states. Well, then the encoding only prepares another state. Obviously, for every m, I can just choose rho m is this encoding here. So this is a state on a to the n. And d is supposed to take the output of these, detect these quantum systems and give me, well, a state, but without loss of generality, it's one of these basis states. There is no harm in going back to the basis state. So it's really a POVM. A measurement with some kind of positive operators. And so let's write the success probability. This is the probability that you actually that m hat is equal to m, so that's what I mean here. The rho hat is simply a basis state. And so assuming that the message is chosen uniformly, so how many messages do I actually have? Let's say this goes from 1 to some big N, 1 over N. And then I just need to look at, so in which cases do I actually say the right thing? So this is the output state I get is this N tensor N over rho M. And then I'm subjecting it to this measurement, so it's this guy. So one of the constraints, so this is a demand on this set of on these code words, which are really quantum states, and the decoder, this should be larger than 1 minus epsilon. And then I can, so this is then basically how you formalize this kind of objective. This maximum n under this constraint, I call it n of little n at epsilon. Fixing the channel. I mean, obviously the channel is, as I said, it's given to us. It's something that we have to work with. So this is the error here. And of course, we would like this to be larger than 0, but in practice, we would, of course, I mean, the way you define things, we would like this epsilon going to 1. So, for example, then the capacity, sorry, we're interested in the rate of this kind of thing, right? And then sort of Nielsen-Schwang or Cover-Thomas type basic cost information theory, they tell you, okay, now you should use n going to infinity many channels, and you should let epsilon go to 0, because that corresponds to asymptotically faithful communication. And this is called the capacity. So if I write this mathematically, I do this just to annoy you. I can write it as a limit, but it's actually an infimum, because the smaller epsilon, the smaller this thing is. Then I take the limit of the rate. And unfortunately, I don't really know if this limit exists, so I have to use some kind of accumulation point. So we can choose the lim sup or the lim inf. Let's be nasty and just put the lim inf as n goes to infinity. And so this is how in kind of serious textbooks you find the definition of the capacity. Okay. So for the private, as I said, we have this extra constraint that the message should be independent of, the output of the complementary channel should be independent of the message. So we need in addition something like this. So what kind of distance measure do we choose for the states? For this discussion, let's use the trace norm of rho m. So this is what the eavesdropper sees, minus omega 0. Let's take a 1/2 sum of let's put it in n again. So you see, well, okay, maybe I shouldn't dwell on this too much. So I'm just assuming that the messages are sent with uniformly. And so that's why I'm taking the average here. So that it allows for the fact that, for example, for some message, this probability that m is sent and m is also decoded correctly is very small. But maybe but it means that there are a few of them, because on average, this probability should be large. Same here. So there could be some messages that give a lot of information to the eavesdropper, but they must be rare. So I want that this is less than or equal to delta. So this is another constraint. And then we have the maximum n, let's call that, just to have different notation for the private one, n epsilon delta. And so clearly this is less than n of n epsilon, because I just have to drop this extra constraint.
What is small n is there, number of users of the channel?
Yes. Oh yeah. Which one? This one?
Yes.
This is number of messages.
You can say that's the dimension of capital S.
Yeah. Yes, yeah. Yeah, actually you're right. Maybe I should do it like this. Okay. And then, well, okay, for the we can do a similar thing for the quantum capacity. Unfortunately, then, of course, for each of these types of information, I have to think precisely what is the notion of approximation that I want to use. So there is not really an error probability, because I cannot just compare the messages. So I use some kind of fidelity measure. So the quantum one, this is what I want to demand is something similar to this average error. So let's put here a maximally entangled state. So that means I need another reference system of the same dimension here. And so then I get some kind of output state sigma, and I would like that this is close to this maximally entangled state.
Could you please explain the constraint again? Describe it.
So, I don't know if you can read it from back there, but so in here I have the trace distance between the output and this omega 0. So the output, of course, depends on m. And omega 0 is a constant. So for a given m, this is the probability. This is the maximum probability with which you can distinguish the true output state from this omega 0. So that if that's small, well, sorry, it's the bias. It quantifies how well you can distinguish the state from this omega 0, right? Under the most general measurement. So this should be small. That's the idea. So that means that the eavesdropper gets no information. And I'm just summing it over all. I just take the average over all messages. So this should be. This somehow captures this idea that the eavesdropper gets essentially always omega 0, whatever the message is. So this is the idea of having no information.
What is the subscript of phi?
Max. Of course, it's a maximally entangled state of the dimension of S, right? So, and for this one here, let's use fidelity of sigma and this phi max, which is the square root of the overlap. So this I would like to have it larger than square root 1 minus epsilon squared. So why this is this is the demand. So this just to have it. I mean, I'm using not the trace distance but something else here, just to have it already there for next week when I have to talk about this thing again. So this is 1 minus f squared. This should be less than or equal than epsilon. And this is called purified distance. And it is actually a metric on the states. So when you define the fidelity, when you extend the definition to mixed states, then this one here gives you a metric on the states.
So why are you defining in terms of maximally entangled state instead of just comparing the input and the output with respect to something else?
Well, but on which state? I mean, okay, I could do average like this one. Maybe are you saying that I should take maybe integral over? Yeah, you could do that too. It's equivalent, actually. I mean, there is a relation between this epsilon and the epsilon that you get when you integrate over the uniform distribution over pure states here, for example, and compare with and take the fidelity. There are many different ways. I mean, of course, I could also use the trace distance here. Actually, it turns out this 1/2 rho minus sigma is less than or equal to this purified distance. So, sorry, it's phi max. So also the trace distance is small in this case.
But this is a stronger criteria than the one which is mentioning, like the epsilon for this.
Yeah.
Sending entanglement is much stronger.
Well, it's not so much different actually. I mean, you get a different quantification. I mean, but it's on the same level as this one. I mean, the norms are related. So, for example, this also, if I would choose the trace distance, I can relate it to the purified distance. I mean, it goes like 1 minus, I think it's the fidelity. Sorry. Are you sure? I have the square root already here, so. So I tell you something. So of course, yeah, this fidelity is a beautiful subject because you can spend a lot of time just fighting each other's conventions. So why do I take the square root here? Because in this way, it has the character of the cosine of an angle. So if sigma is pure, this is just the cosine of the angle between the things. And so the purified distance in that sense is the sine of the angle. So when you take the squares, okay, this gets lost. So that's so nice. So it's something like this, I believe. So this is again lower bounded in terms of p. Maybe something like half p or so. Or let's do it like this. I don't want to bother about it now. I mean, you just have to use the definition of the p. So anyway, the point I want to make is these are two and not the only two ways of quantifying the error. And I just choose this one. So and it's actually a nice one which ties in with some things that you heard during Graham's lecture, which is this fundamental intuition connecting communication and quantum communication and creation of entanglement, or that goes further, also private communication and the creation of secret key. So one of the major tasks that we can, I mean, why do we want to send quantum states? Well, one of the major reasons why you might want to do this is because it allows you to distribute entanglement. And this is exactly, so I'm just using this objective as my way of quantifying the error. And whatever the code does, it will allow me to create entanglement up to some fidelity. Okay, so this took me much longer than I wanted. Yeah, so I can again study this one here, and then again I have a capacity, which now is the quantum capacity. So this is the inf of epsilon, the limit of n, or the inf, and the 1 over n times log L of n epsilon. So this is just to, this notation is just to introduce, just sort of to drive it home that the number of qubits you can send, or the number of classical bits you can send under these various restrictions, it depends, of course, on n and on epsilon. However, in the usual theory, we somehow, I mean, for a good reason, we try to get rid of both of these dependencies. And we only look at this limit. So if you want for example, some formulas that we had seen on the board during the last few days for each of these, for actually some of these capacities, I mean, they rely on this idea that you do want to use the channel asymptotically many times, and the error should go to 0. So the fundamental question that I want to address, if you want, I mean, this sort of a question that once you get into the spirit of communicating is, well, so what happens if epsilon is non-zero? Or what happens if n is not infinity? So this is basically what I'm talking about now and for the rest of the, I mean, also next week. So and so this is a, in a way, this is a very good way of starting information theory, because what we will do is I just want to show you how to use some very simple tools to get at least some upper bounds in terms of, let's say, nice quantities. I mean, the whole, I mean, these are just definitions, right? I mean, this doesn't tell you anything. I mean, this doesn't even tell you when this capacity is 0 or non-zero a priori. You need, and in fact, from Graham's lectures and from what Fernando said, I think you typically need some kind of ad hoc argument to for this particular channel, for example, to know why Q should be 0, or why should P is equal to 0 or non-zero, and how large can it be. So let's start. So what I just want to show you that we can actually get some bounds that work for finite epsilon and finite n. But they lead to more questions themselves. So bounds on Q, P, and C. So what we actually do is we really bound these numbers, n of n epsilon, m of n epsilon delta, and L of n epsilon. Oh yeah, so by the way, so of course just a little note. So L of n epsilon, this is less than or equal to m of n epsilon epsilon. And I said, this one I had somewhere here. So these are more precise expressions of the fact that if you can communicate quantum information, then you can send private information. And if you can send private information, then you can send classical information by just forgetting about the privacy. Say it again, please.
Bounds on C, P, and Q. You have it here. Here. No.
Oh, you mean this
No,
one
I
here?
just-
Yeah. Good point. Yes. So this one is obvious. You just forget about privacy condition. This one here, it's not difficult. Maybe we leave it for later. So as I said, these are the expressions of the fact that Q is less than or equal to P is less than or equal to C. But they are more precise because they refer to finite n, and they also refer to arbitrary errors. So we can compare, we can also compare on the finite regime. That's the point. And these bounds, these are called weak converses. So for these weak converses, I need just some tools, but I think we had them already, at least Fernando, I heard Fernando talking about them, and I assume he introduced them. So we need some the tools are strong subadditivity and Farnes inequality. And actually, I will put another one that I call Fano. Actually, not I call it. I mean, people call it Fano. Fano, I forget the first name of the guy, but he was one of the first disciples of Shannon at MIT. So, now, first, how how do you want the denote the entropy? Huh? Should I go with the S or with the H? I mean, I probably, if whatever you say, I probably will slip into the S sooner or later. But okay. So for a three-party state, we have S of AB plus S of BC larger than S of B plus S of ABC. However, from the information theory point of view, it's good to have some kind of equivalent formulations. I mean, these are just algebraic reformulations of the same thing. For example, this one here, mutual information between A and B is less than or equal to the mutual information between A and BC. Where, I don't know, I guess we had mutual information written down. So this is, mutual information is simply the sum of the local entropies minus the joint entropy. And so if you do this here, then you see there's one term that cancels and you get back to this one here. Equivalently, the conditional entropy is related by this way. And so this is, again, it's just something like this one here. Actually, as a matter of fact, this is the form of the inequality in which you find it originally in the paper by Lieb and Ruskay in 1973, I believe. And yeah, so another equivalent form, and I think this was something that I saw in Graham's lecture just before. If you have just a two-party state, rho AB, and you have a C completely positive and trace-preserving map, I don't know, M, that goes from B to C, so that we can write down omega is identity tensor M acting on rho, so this is omega AC now. Then the mutual information of A, B is larger than the or equal to the information between A and C. So this is with respect to state rho, and this is with respect to state omega. Yeah, now I filled all this board with strong subadditivity, but okay, fine. So the next one we need is Fannes. This is the continuity of the entropy function. So in the trace distance, if rho and sigma are close in trace distance, and I'm using here a formulation that I found in a recent paper of Konrad Audenard. Yeah, why not? Then the entropies, the von Neumann entropies cannot differ too much. Epsilon log we. Well, okay, I just write D. I hope you get the, so this is simply the dimension of Hilbert space plus a binary entropy of epsilon and 1 minus epsilon. And so this is, let's say, tool number 1 here. 2. And a variation of this Fannes inequality, which is actually is an older one, and it's a more specific one that goes back to, as I said, this Manfano, that is only about random variables. You have random variables that's called an M and M hat, because that's how we want to use it. And the probability that M is different from M hat is less than epsilon. Let's say it's equal to epsilon. Then now this is an age, because these are just classical ones, the entropy, the conditional entropy of m given m hat. So this is your uncertainty of m if you know m hat, is less than epsilon log, now, I need from 1 log n plus the same. And so these m are from 1 to some capital M, let's say. So of course we always have a conflict in lectures like this, what you actually prove and what you show. So I wanted to say, well, now I want to show you how you prove whole-level bound, but we should of course also appreciate what I ask you to believe already. So this one is well known to be a big hammer. So I don't want to prove it basically because it will require a completely, at least one lecture, I guess, to get all the tools ready. There are many different proofs of it. That's nice. And many different ways of looking at it. This one is essentially elementary. If you're not particularly picky about getting some suboptimal constant, maybe a 2 epsilon here or an extra term here, then it's really simple. And also this one is elementary. So this of course is a highly non-trivial thing, but so how do we do this? Well, we look at the code. So I want to do this at least once. I guess I have some material prepared for the other capacities, but well, okay. No, so how do we do this? No, it's from 1 to some n, and it's uniform, right? So this is what I want to do. So m gives rise to some machine that prepares rho m. And this goes into the channel, while actually our channel, as we know, is just some tensor product of some elementary CP map. And then we have, so this here is on b to the n, and then we have this decoding map that gives us m hat. Let's define one of these typical joint states that kind of keep track of the correlation between the input and the output. So this is a 1 over n sum m. This I call the X system. And then I have the channel output of rho m. I have a rho x hat, which is the same state after applying the decoder. So I can actually write it as such a thing, identity tensor D acting on this rho xp. And so this is going to be 1 over n sum over m. And then I need sum over m hat, probability of m hat conditioned on m. So I don't want to write this out here. This probability, of course, is some trace of operators, right? It's the output state, and there's a P of m that I don't want to repeat now. Okay, so what do we know about it? So I want to assume that we have a code with these parameters. We have this n and this epsilon. So probability of m hat different from m is less than or equal to epsilon. And so this is what we get. So from Fano, I have that the entropy no, let's do it the other way around. We start with this strong subadditivity. So the mutual information between x and En is larger or equal than the mutual information between x and x hat. So this is strong subadditivity. Why? Because I'm just acting with a map on this system and I get x hat. And this is one of my formulations of strong subadditivity. So this is the entropy of x minus the conditional entropy. But these are just random variables here, so I can as well write m and m hat here. And so this one here, I am assuming it's uniform, so it's just log of the number of messages. And for this one, I use Fano. So this is larger than log n minus epsilon log n minus, well, okay, let's look at this Fano. Let's simplify things a little bit. This is just a binary entropy, so it's bounded by a constant. Depending on the base of your logarithm, which for me is 2, this can be at most 1. So that's it. So this, I'm just writing it out now. What do we get? I want to bound the rate, right? So I want to get 1 over n log capital of n epsilon is less than or equal to, well, I just have to bring everything on the other side. And so this is less than or equal to 1 over 1 minus epsilon, 1 over n chi of n to the tensor power little n plus order 1 over n. So this chi here, we also had this on the board a few times already. This is simply the maximum over mutual informations of this type for states that look a little bit like this one here. So rho xb should be some px something like this here. Yeah, so at this point I'm just forgetting about the fact that how I got this rho xb, that it had to be a uniform distribution and it had to be a code. All I remember is, well, okay, it's some probability distribution over some orthogonal labels, and there are some states. And so this Holevo capacity is defined as the maximum over all these ensembles. Okay, so what does it buy us? When n goes to infinity, this goes away. So independent of epsilon, except when epsilon is equal to 1. Should we worry about this? I think not, because epsilon equal to 1 means that your success probability is at least 0, which I suppose you know how to do that. And there's no restriction on the rate in this case. So we can hope to get a non-trivial bound anyway, only if epsilon is strictly less than 1. Okay, so then this is constant, and n goes to infinity, so this goes away. This one here is more interesting. This one is the information theory part. There's no mention of epsilons anymore. It's as it's supposed to be in Shannon's theory. It's a kind of entropies and maximization of some entropies, fine. This is not nice, because this is bigger than 1. And well, it depends on epsilon. So it decreases when epsilon decreases. So we should, to get so let's take the limit of n going to infinity. So this is less than or equal to 1 over n, 1 over 1 minus epsilon. And then, yeah, do I write it? Limit 1 over n, chi of n, and so on. I guess I'm writing too small again, no? Yeah, beautifully. Okay, I guess you copied this, so I can remove the quotes. Doesn't matter very much. So why are we not really happy with this? Well, first of all, because we should compare with what we know from the other side. So this is called HSW theorem, I guess. Rolevo, Schumacher, and Westmoreland. They show that the capacity of n is larger than chi of n. And indeed, it's larger than this limit, 1 of chi over. So what you can show is that C of n, the log of n epsilon is larger than chi of this n tensor n. Oh. Now let me put it like this. N times minus order square root n for fixed epsilon. So this is what the proofs show you. So in the limit that epsilon goes to 0, that means we actually bound the capacity from above and from below. So this is typical information theory, of course. We have an existence proof, which, I mean, this is more or less nasty. As I promised, I won't go into this. There are different ways of showing this, but they all have the characteristic that the error goes to 0 already. And in this limit, we can achieve this rate. And in the limit that epsilon goes to 0, we also see that this regularization of chi cannot be beaten by anything. However, for epsilon non-zero, it's strictly bigger. So this is somehow the question that leads from that distinguishes. Sorry, that's the hallmark of the strong converse. That what you would like is a bound that doesn't depend in the same way on epsilon. Of course, the bound in some way it has to depend on epsilon. If you allow bigger error, of course you can send more information because you're tolerating more. But that it affects the rate proportionally. This is what we don't like. Or rather, we would like to know, is that real or not? So this is kind of question. And I can tell you, so whenever proving a strong converse means that you show that there is no such trade-off. So I will get to that in a bit. Should I do this now for the private capacity? Well, maybe I just write it down. So you get log of m n epsilon delta. So I work this out somewhere here. Yeah, whatever. So 1 minus epsilon minus some constant of delta. This is less than or equal to plus another constant. I hope that this is more or less correct. So this refers now to a three-party state, which looks like this. Yeah, why not? X, Bn, En is sum of all of these guys. And we have V tensor N, rho M, V dagger tensor N. Yeah, so obviously for the private capacity, we also have to somehow say something about the environment. And for a good code, from this previous discussion, we see that this is essentially log number of messages. And this one here, well, because the message and the output of Eve are almost independent, this is almost close to 0. And so you can use, again, Fannes inequality for this one. So there's kind of here's a hint. So we should use, to get precise dependence here, we use an improvement of this Fannes inequality that's due to Alitzky and Fannes, which is rho AB and sigma AB are bipartite states. Then the conditional entropy of A given B of rho minus the same thing for sigma, they are related by some constant, I guess.
What is that norm there? Is the norm representing the singular values?
This is the trace norm, yeah. Yeah, exactly. The spectral norm, I guess some people call it.
What multiplies the 3?
Sorry?
That's 3.
This one?
Yeah. Just 3.
It's just number 3. Well, 3 log 2. Again, it depends on which basis of the log you choose, but since I choose... So for me, the binary entropy can be at most 1, so it comes from such things. So I don't know if we wrote down anything like this during this week, but so if you maximize this expression of entropies over all ensembles, even with different probabilities here, then this is what we call P1. And so you see you get a similar bound again. And for quantum, it's something like this here. Should be similar. Maybe 2. Maybe have a 2 epsilon. Yeah. The precise constants shouldn't matter too much because again we are interested in the limit of epsilon going to 0, right? So if it's 8 epsilon or 120 epsilon, you shouldn't bother too much. I guess something like this here. Yeah, okay, so this is equal to S of minus S of AN conditional BN plus 2. So then this is less than or equal to Q1 of the channel N times plus 2. And again, so you divide by N, you bring the epsilon on the other side, and you get bound that looks a lot like this. In both of these cases, I wrote these bounds because, as it turns out, they are also achievable in the limit of epsilon going to 0. So there is a completely separate part of the proof. Obviously, this is very simple. All I'm using are some kind of monotonicity properties. From the other side, to get larger or equal, you have to show in some way that these integers are big. So you have to show there exists a protocol that does get so and so many bits across. Turns out there are protocols that get you this number of bits, minus square root n, or the square root n, and also here with the number of qubits, in the limit of epsilon going to 0. So the bound, however, is loose when epsilon is non-zero. So we only get the capacity in the sense that from below, it's nice that we can let epsilon go to 0 because obviously that's what we want. From above, it opens up this possibility that maybe allowing some small error, we might increase the rate a little bit. And so that would be a very attractive thought in a certain sense, because you could try to trade off the reliability of your communication with the amount you can send. I mean, it's clear that there is not very much space for this, right? So I mean, I don't know what is acceptable error for you. It depends probably on the importance of the message. Let's say it's the probability that you win in the lottery, that you buy one token for the lottery and you win. So it's something like 10 to the minus 9 or 10 to the minus 10. So if you think this is too improbable to happen anyway, you put it here, and so you see that, okay, there is a fraction of 10 to the minus 9 that you can increase the capacity. So it doesn't look like much. But okay, it might depend on the context. Maybe you have other contexts where you are happier. Then there are these bounds which have these constant factors in front. So they already blow up. Even a small error can be bigger. So at this point, it's more of a fundamental question, let's say. So I want to consider it as a fundamental problem. Is there a rate error trade-off? And I want to show you in some cases where there isn't. So how am I doing with the time? So I think I'm very slow today. But it's fine because I don't have really that much to calculate. So yeah, so this is the thing. This is achievable. And also this one is achievable. Boo. Okay, let me start again over here. So the way I define the errors, they are always between 0 and 1. I mean, for the classical capacity, it's a probability. But also for these other things, for the private, for the quantum, you can think of them as probabilities. There are some numbers between 0 and 1. So in the limit of large block length, of n going to infinity, so what do we know about the error? Well, okay, by definition, we have here, we have it 0. I mean, asymptotically, it's arbitrarily small. So that's why I draw it as 0. And in fact, this is maybe an interesting, it's an interesting observation. All these existence proofs of codes, they show you even more. They show that epsilon goes 2 to the minus constant times n in delta 2. So you can make them both disappear, go to 0 exponentially if you're away from the capacity. And the weak converse, so all these bounds here, we call them weak converses, they just give us something like this here. Above the capacity, you can read this the other way around. If the rate is bigger than this limit here, which we know is the capacity, then epsilon cannot go to 0. There is some kind of lower bound, but it depends on these two numbers, on the rate and the capacity. So this is this region that we are interested in, this one close, slightly bigger but close to the capacity. We would like to know what does actually happen with the error. And so this line here, this would be a strong converse. Yeah.
So are we looking at the, say for example, the quantum case,
Yeah.
are we looking at the function log n of small n comma epsilon,
Yes.
n tending to infinity,
Yeah.
versus log n infinity comma 0? Is that what you are looking at?
Yeah, well, yeah, that's what I'm showing here basically. Yeah, so I'm fixing epsilon, and I'm interested in the limit of n going to infinity, or maybe you can also think of it. Just look at protocols. In the limit of n going to infinity, it will have some rate, it will have some error, so you're somehow in this plane. And our question is, which points in the plane are accessible? So this is I'm probably way too pedagogical here. A line of this sort here, this is what we just proved. I guess it actually should be probably a straight. It should be a finite slope here. Non-zero slope. This is what I just outlined over there using strong subadditivity. This is from below the capacity, obviously all this region is accessible because we can always add some error, but we can get all the way down to 0. So if we could prove a strong converse, and I will show you in a second how to do this for the simplest case of a noiseless channel, it shows that what this amounts to is saying that as soon as you're on the other side of the capacity, your error goes to 1. It's as big as possible. It's as big as it can be. Yeah, so in the classical communication case, error is 1 minus success probability. So I'm saying the probability that you get the message goes to 0. Makes a jump. So there's no space in this diagram. Whereas the weak converse, it allows that there might be some life here, some big error, but also big rate, right? So in a certain sense, if that happens, we would. I want to go back to Shannon's days. In those days, people would call a channel that doesn't have this jump behavior a channel without capacity, because they would argue you shouldn't characterize its performance by a single number. The performance is given by this curve here. You want to know how the two parameters trade against each other. So the strong converse is a statement that there is no such trade-off. That really everything is just encoded in this one number. That happens when there's a jump, and that's it. What we will see from proving strong converse is it actually gives us a little bit more, because again, for simplification, I looked at the limit of n going to infinity. Well, in practice, you always get, even in these very simple considerations here, you get relations that are valid for finite n and epsilon. And so that allows you also to zoom in a little bit what's happening close to the capacity. You can answer the question in a certain sense, what happens if the rate is equal to the capacity? Even though I will not go into all the details of this, but you can see from the proofs that there is some kind of scope. So maybe I just want to write this down at some point. What we would like to show is for all epsilon between 0 and 1, that this is equal to n times the capacity plus little o of n. Yeah, so this is another way of saying, getting this jump behavior. And so little o of n is just saying, well, asymptotically, when I divide by n, this goes to 0. In practice, we also learn about this little o of n. How does it actually go with n? How does it depend on epsilon? So these are things that you can also extract from a more detailed analysis. So you should look at it this way. All I did here was using some inequalities, and then it turns out we were lucky that in the correct regime of epsilon going to 0, the inequalities are not so bad. Actually, asymptotically, they give you the right thing. What you really should do is you should really try to understand this kind of quantity from first principles. You would like to, if you have to bound it, try to bound it as tight as possible. And so this is kind of the second theme of these strong converses that is maybe the more appealing one, rather than some kind of phase transition like jump. It's a more detailed understanding of the maximum performance of the channel for finite n in epsilon. Okay, so this is noiseless qubit. For this one, you should be able to work out either these formulas that I gave you, or in some other way. We know that Q and P and C are all 1. So as a matter of fact, n of n epsilon is larger than, well, actually, we put L of n epsilon is larger than L of n0, because obviously I get the tightest bound when the tightest constraint when the error is smallest, which is 2 to the n. Obviously, if I have n uses of the channel, I can send 2 to the n dimensions in some way by identifying this space with these n qubits. And the m is somewhere in between, but I don't care about it. So let's bound this one here. Okay, so we have a code. We have some rho m's, states, and we have dm positive. Sum of this dm is equal to the identity. Which identity? On the qubit tensor power n. And we have that the error probability is small. So 1 minus epsilon is less than or equal than the success probability. And this is 1 over n . And again, I'm just doing a bound, right? All I have to do is get an inequality. So I'm showing here a folk argument. I have no idea where this comes from originally, but it's very nice and simple. I want an upper bound on this here, I guess. So I remember that this is a density operator, so its eigenvalues are between 0 and 1. And that means this trace of rho times d is upper bound by the trace of dm. Doesn't look like a very good bound, but who cares, right? I mean, so the largest eigenvalue is, this is upper bound by the identity, so I can just put it here. Now the sum of this dm is the identity, so the sum of the traces is the trace of the identity, so I get 2 to the n divided by capital N. Yeah, so I get that n of n epsilon is less than or equal to 1 over 1 minus epsilon 2 to the n. And that looks suspiciously like such a thing, except it isn't. Because here I have the log of the messages times 1 over epsilon. 1 over 1 minus epsilon. Here's the messages themselves. So if I look at the log, this is less than n plus, and then log 1 over 1 minus epsilon. That's an additive extra term. So clearly, if we divide by n and let it go to infinity, then this will go away. And so this is the kind of statement that we want. So this is the proof of strong converse for the identity channel. I mean, it's simple enough. Should really look at the time. So I use a few more minutes. So obviously, this argument is extremely primitive, and you can see that it only works for some primitive channels. Why? Because we have no noise. So the input state here is equal to the output state because it's noiseless channel. And so then we can use this bound. If we don't have that, then we are a bit in trouble. So we would need some kind of bound on the largest eigenvalue here, and okay, it's not likely to give you the capacity because the capacity is in terms of entropy. The entropy depends on all the eigenvalues non-trivially. It cannot be just the largest one. Okay, nevertheless, it gives us something, namely, for example, it tells us that the error probability has to go to 1, at least if the rate is big enough. So why is that? So let's say, so assume that n can be simulated by the noiseless channel, which it always can at rate R0. So what I mean by this is that Alice and Bob, they can, by using this identity channel k times, let's say, and doing some suitable pre- and post-processing, they can generate something which looks like n uses of the channel. So, and again, of course, I should have to specify a norm in which, or a metric in which I compare the channels, but I don't do this now. I mean, I hope this is intuitive enough that we choose an appropriate one that takes care of this. What this metric is supposed to do is it should quantify how well you can distinguish that you're truly given n instances of this box with n, or some more complicated contraption where there's this encoding and decoding of Alice and Bob inside that pretends to be n. Right? So it's a distinguishability measure again. And k over n goes to R0 as n goes to infinity. So then for rate, sorry, how does it go? No. Which way do I want to? So what I want to say is if I want to use the channel n at rate larger than, to communicate at rates larger than R0. So for n, for log n equal to nr and r bigger than R0, epsilon goes to 1 by the same argument. Why? Because if I have a code that just puts some extra encoding and decoding here to make a noiseless channel, but then I can just append this to this simulation. I put something here and something here, which just makes some big operation of Alice. There's the encoding of the information for n, then another encoding to do the simulation. Same with the decoding. So there's this D that gets me the output of channel n, and then Alice, according to the definition of the capacity, must have some kind of decoding. So taking these two operations, two of Alice, two of Bob together, that's just another code for the identity channel now. Right? I'm just sending information via the noiseless channel, and I know that I cannot go above this k much.
So defining this R0, is there some optimization over this encoding and decoding?
Yes, yeah. So I mean, at this point, I just want to show that whatever simulation you have, if you happen to be able to construct something at rate r, you can do something with it. So in this, for example, so the problem there is typically, so this is, maybe I should write this here. Typically, R0 is bigger than the capacity of the channel. So we do not get a strong converse in this way. I mean, for some sufficiently big rate, the error will go to 1, fine. But I want it to happen exactly at the capacity. So there are some very, I mean, obviously we are lucky for the noiseless channel. I mean, this is basically what I just showed you here. And apart from that, I don't know too many other channels for which it happens. So one good example, that's the pure loss bosonic channel. So the how do you call this? The quantum limited attenuator. So for that one, we know the capacity, and it happens that we have a simulation of the same rate. So I guess I should not spend too much time on this. So this is in a paper that was a small note that I wrote with Mark Wilde some time ago. Okay, I forget the reference. So, but the simulation argument is very powerful, and I want to make it a bit more applicable. Let's say I want to present another way of proving this one here. That uses. I mean, this is some kind of an ad hoc argument, just using the fact that the sum of the POV elements has to be 1. There is another nice argument that uses just causality, in the sense that if you don't get a communication, you cannot guess the message better than 1 over the number of messages. Sorry, actually it's not for the same channel, it's almost the same one. So let's do another, it's just for the classical capacity of the completely dephasing channel. So ID bar does the following. It just it removes all the off-diagonal elements. Yeah, so clearly the capacity of this one is also 1. It cannot be bigger than the noiseless channel 1 to simulate. This one is rate 1, for example. And of course, I can use the computational basis states to communicate noiselessly. So the claim is, so the capacity is equal to 1, even when I allow assistance by things like entanglement, or more generally, any kind of device that it itself doesn't signal. So of course, that requires extending the concept of code, which I will not write down at the moment. So how does it go? So we have our n users of this channel, which means that the receiver gets 1 out. So op gets 1 out of 2 to the n. Let's call it transmissions. Yeah, so that's what he sees on the channel output. From that and from these extra resources, for example, the entangled state or the no signaling PR boxes, whatever you like, from these two things, he wants to infer the message. Yeah? So M, which goes from 1 to big N, from this, and no signaling resource. So now you compare. Now you let Bob basically try to do this without having access to the output of the channel. So anyway, so the probability that M hat is different from M, or is equal to M, is larger than this epsilon, yeah? So now, what kind of probability can we obtain if Bob doesn't wait for the transmission? So if Bob guesses the output, well, in that case, he has a chance of 2 to the minus n of getting it right. And on the assumption he gets it right, he can follow the protocol in this point here and get a large probability of success. So probability of, now we call it guess, M, is larger than 1 minus epsilon times 2 to the minus n. Yeah, I hope that's convincing. But this is done without using the channel at all, only accessing the no signaling correlation, which means that this cannot be bigger than 1 over n. And so we get the same bound again. Now, of course, for classical channel, I was using the fact that there is only a discrete set of possible outputs for the channel. That's very important. Yeah, so I get again that n is less or equal to 1 over 1 minus epsilon 2 to the n. But this is noiseless channel assisted by whatever. Entanglement, no signaling correlation, and so on. In a sense, you can even modify this proof to include things that signal but in the wrong direction. So it's feedback. If there is a channel from Bob to Alice, that also doesn't increase the capacity. So it's, you can also make an argument of this type in the presence of feedback. So the nice thing about these extra resources is that, should I stop here? Maybe I should stop. I can continue this also on Monday.
Until Monday.
Huh?
You can continue until Monday.
I can continue on Monday. I will continue doing completely different things until then. I hope that's okay. So this simulation, this causality argument, because it works for assisting resources, it applies to other capacities. So a corollary that at least I want to write down, so the CE of n, which is the entanglement-assisted capacity of n, which is given by this very simple formula. It's the maximum mutual information maximum mutual information between the input and the output of the channel in a certain sense. This satisfies the strong converse. And why? The proof uses the quantum reverse Shannon theorem. By the quantum reverse Shannon theorem, n can be simulated, efficiently simulated. By the classical channel, assisted by entanglement. So efficiently meaning at the same rate. We can simulate the channel n, or many copies of channel n, using appropriate entanglement, using n times the C sub e instances of the noiseless classical channel. And so any code to transmit information via n, by plugging it together with the simulation, becomes a code for transmitting information via the noiseless classical channel. And for n uses, or n times C sub e uses, we have this very strong bound on how much information we can actually transmit or communicate. And this bound is robust under allowing this extra entanglement. This is the main point, because of the simulation uses entanglement. And we can even allow entanglement-assisted code, which is, of course, the main point here. So I will stop here. So this is kind of the first thing. There is one capacity in the world of quantum information that we understand and which has a strong converse for a very simple reason. Of course, I mean, this, again, I was cheating massively because both of the proof of this formula here and the proof of this quantum reverse chain theorem are not entirely trivial. They require a bit of work. But conceptually, this is the main message that you should take home. There is this simulation. And it allows you to go back to the identity channel for which you have this ad hoc kind of argument. Okay, I stop here. Sorry. Yes.
Just to clarify the example of the quantum limited attenuator. So
Yeah.
the fact that R naught turns out to be the same as the capacity
Yeah.
implies a strong converse in it.
Yes, yeah, exactly. I think I could have written something like this for the that log n of n epsilon is less than or equal r plus order 1 over n. This is what is R0. It just puts a bound. So, and the characteristic is the bound on the right-hand side depends in some weak way on epsilon, but it goes away when n is big enough. Yeah, exactly. So as soon as you know that you can get down to the capacity. So the reason for the attenuator is that what does the attenuator do? It loses a fraction of the photons. So when you have a constraint on the input power, that is equivalent to a constraint on the number of photons that you can use over the n uses, over the n channels. So kind of there is a number of proportional to n of photons in this whole n mode system, and all you have to show is that the output of this attenuator, of course, it actually when you look at it, it has in the number basis it has contributions from all different numbers up to the one that you had in the input, but for the most part, the typical part of the amplitude lives on a number of photons which is much smaller than the input. It's exactly when you have this transmissivity lambda and you have input photon s, then the output expected number of photons is lambda times ns, and well, this when you use a large number of modes, where you can distribute the number of the photon in some way, then this becomes a sort of a high probability statement. You can show that most of the amplitude of the output state lives in the space of bounded number of photons. That's the important part. And so then it happens that this is actually the dimensionality of the space is the capacity. It's just that's how it is. And so it's for very trivial reasons, actually. And yeah, but I wanted to show it just to say that this simulation argument is not completely useless, and you get it also here from the flat, I guess. So if there are no more questions, let's go for lunch.